Okay, so we're going to talk about a new concept called charge density. So far, we've really just been thinking about charge of individual point particles and maybe a collection of point particles, charged point particles, where you can calculate the electric field at a given point using all of the different electric fields produced by those charges. But now we're going to start thinking about what if you want to distribute that charge uniformly or non-uniformly over an object. We'll start to talk about charge density. So when you have charge spread out over an object, we can describe the distribution of charge using charge density. This is really similar to mass density, but instead of thinking about mass, we're thinking about charge. Where is the charge located within this object? So in one dimension, we're going to use the symbol lambda to describe a one-dimensional or linear charge density. It's given by this equation here. Lambda is equal to dq over dx. dq is an infinitesimal amount of charge, and then dx is an infinitesimal length. I've chosen x as my coordinate here. You could have just as easily chosen y, z, or r, or something like that. So lambda is dq over dx. If the charge density is uniform, the charge is uniformly distributed over the object, you can calculate it as the total charge divided by the total length. Here's a quick and dirty derivation of this calculation here. So I've got dq is equal to lambda dx. I got there by multiplying dx on both sides of this equation. So dq is equal to lambda dx. You can integrate both sides. When you integrate the left-hand side of dq, you end up with the total charge q. So I'm representing the total charge using the capital Q there. And then when you integrate the right-hand side, because lambda does not depend on x, you can pull lambda out of the integral, and then you're just integrating over the length of whatever piece you are looking at. So here I've got q, the total charge is equal to lambda times L, the length of your one-dimensional line there. Then I can rearrange and I can see that lambda is equal to the total charge divided by the total length. You can only do this when the charge density is uniform though, so watch out for that if you have a non-uniform charge density. So to sort of summarize the different charge densities that we're going to be working with, our one-dimensional linear charge density is dq over dx. A two-dimensional surface charge density we'll represent using the symbol sigma. That's dq over dA, where dA is an infinitesimal area. And then a three-dimensional volume of charge, we'll represent this using the symbol rho, which is dq over dV, where dV is an infinitesimal volume.